All right, how's it going? So how'd the ODP end up? That was kind of a weirder one, right? So here's a solution. You're past a pointer to the first node, which I'm calling N. So this looks like this. So temp equals N arrow next. And then N next equals temp next. I think it was just 3 nodes, right? So temp equals N next, right? The way I draw these pictures, I'm going to label this temp because it's the node that's being pointed to by the next field of N. And then temp arrow next is the node that temp points to, just like temp is N arrow next. And so when I set N arrow next equal to temp arrow next, what I'm doing is changing this pointer to be the address of that node, right? So that's skipping over. But this is potentially confusing too, right? Because if I'm thinking of this node as N arrow next, and I say N arrow next equals temp arrow next, it feels like maybe I'm replacing this node with that node or copying it or something like that, right? It's not. Really think of N arrow next as a piece of this node, but it points to that node. So be a little careful with thinking of these things like that. Right? This is this confusion between what's a node and what's a field. But that part of node N arrow next, gets assigned to the value of temp next. Well, temp arrow next is really right here. And that's something that points to that third node. So I'm setting the pointer in N to point to the third node. That's how we're removing temp. And then we're freeing temp at the end. And freeing temp is a little tricky. If after this I say free N arrow next, that's not going to free temp. That's going to free this node, right? Because I've set this to point to the third. So a lot of times you actually need to have something that holds the value of the node you're going to free from memory eventually. But I don't think you had to free it for this one. All right, so last ODP for a little while is 210. And so again, we're starting with a list of 3 nodes, no sentinel node. It's just 3 nodes pointing from one to another. And we're given 2 arguments to edit to. The first is an integer, the second is the address of that first node. And your goal is to insert a new node here instead of deleting. So you basically want to insert a node between the second and third so that you end up with a new list, starting with PTR, the old first node, your new node with a data value of num, and then the old last node. You're just squeezing it in between. And again, it's just call malloc to create this new node, set the data value to num, and then do something with the pointer so that a second node points to your new one points to the third one. So it's just keeping track of what's where. And when you're coding this, right, nothing wrong with saying, you know, first equals PTR, second equals PTR arrow next, third equals second arrow next. So now you've got names for these three nodes. And that makes this a whole lot easier because it should be second arrow next equals new, and new arrow next equals third. Right? So you don't have to be precious with variables. You can make as many variables as you want. And if you're making a variable like struct node star third, it's just a pointer. Right? You don't have to malloc space for it. You're going to set it equal to the address of the third. So do what makes sense. The other thing a few people got caught by, right, if you made the unfortunate choice of calling your executable program edit, and you try to assess that, you get 0 out of 10. Right? Well, that's the wrong ODP at this point, but if it was still 209, you'd still get 0 out of 10. And if you try to run your executable, you get this weird message, right, talking about regular expressions and deprecated things and stuff like that. But the kicker is over here at the end. It mentions user bin edit. So, which edit, user bin edit. Edit is a built-in command. Right, it's on your path, and if you try to assess edit, it's actually trying to assess user bin edit. So you could get around that by saying assess /edit, right? But the easiest thing is just don't use a common name for your ODP. So I've been suggesting, you know, main 201, main 202, main 203. It keeps you away from this problem by just calling it something unique. Same thing with test, right? Test is a built-in command. And so if you try to assess your program and your program is called test, you're probably assessing this built-in command. And that can drive you crazy for a while. All right, so good on the ODP? All right. So let's go through some code for PA1, and then let's talk about how we can use that to work on PA2. And then we'll talk about freeing memory in PA2, and then we'll start talking about the quizzes. I pushed the dates back on the quizzes that are on Canvas, except for one, which I think is due on Friday, and it's a basic question about linked lists. And you should be able to do that one already. So make sure you watch the deadline. All right. So I already showed you my main program, right, which is just a while loop around a process function. Process does whatever your user input asks it to do, and if it returns 0, it means the user wanted to exit. So process is the main workhorse. And buffer is the character string containing the user's command. So first thing I did was I just looked at the first character of buffer to see what kind of command are they asking for. If the first character of buffer is an I, I'm going to see if this is a legal insert command. If it's a P, I'm going to see if it's a legal print command. If it's an S, I'll see if it's a legal search command, and so on. If it's an X, I'm just going to exit from my whole program right here, my process function, with a code of 0, which means, hey, the user has to exit. And if it's anything I don't recognize, I'll give them a help message by calling this usage function. All right, so we've done this before in 224. How do we know if they said insert integer? Well, I'm going to look for an I followed by an integer followed by anything else other than white space. And I'm going to scan that. I'm going to put the integer in num. I'm going to put the anything else in extra. If they just type an I, scanf is going to return a 0. If they type I integer some other stuff, it'll return 2, including if they say like I 2.5, right? The 0.5 will be extra. If they just say I integer, scanf will return 1. So that's the condition I check for, to say, hey, they typed in I followed by a number. So if scanf returns 1, search the list. If search returns 1, tell them it's already in the list. Otherwise, call the add function. And you can save the return from add in a variable and check it. But I just put add in an if, and it said if add returns 1, then print success. Otherwise, it wasn't in the list, but it didn't add. We must be out of memory. So I'll print out no memory available. And if scanf did not return a 1, then they tried to do an insert, but they didn't do it right, so I'll give them a help message. And switch statements you always have to break after each case, otherwise it just goes into the next case. All right, print, I insisted that they follow the P with an enter. You didn't have to do that. So I make sure the next character is a new line. And if it is, then I print out the list. Otherwise, I give them a help message. Search is just like insert, right? Pick up the number. If it's a 1, call search and print out found or not found. Delete, just like insert and search. But before I call delete, I call search to see if the number they're trying to delete is in the list. If it's not, I print the message saying node's not found. Otherwise, call the delete function. And I'm assuming it's going to succeed, because if the node is in the list and my code's written well, delete should delete it. So I'll print out success. Optimistic programming. Okay, otherwise they said D, but it wasn't intelligible, so I give them a help message. And then X is X followed by a new line, return 0. Usage, very complex function, right? This tells them what to do if they're typing in commands that I don't recognize. But it's in one spot, and I can change it, and I can comment it out if it's annoying me and stuff like that. So all of my linked list functions are inside this ll.c. So routines for managing my list. So init you've done in ODPs. Basically element 0, set the next to be null, set valid to be 1, and I flagged the data field with 42 just so I could spot it. And then for all the other entries, just clear the valid flag. And that's the minimum you need to do to initialize your array of struct nodes. Let's look at print. So print, initialize PTR to the first data node. Okay, there's a lot of ways to do this. But I know list bracket 0 is the sentinel. I don't want to print that thing's data. So I set PTR to list bracket 0 next. Okay, list bracket 0 always exists. That's the sentinel. Next will always have some value in it. If the list is completely empty, PTR will be null. If the list has at least one node, one data node, PTR will be the index of that node. So my assignment to PTR is safe, and my while condition is see if PTR is null. And if it is, I'll kick out of my while loop and print a new line. Otherwise, PTR is the first node of the list. I want to print out its data. So I just print list bracket PTR.data, and then move to the next node. Take the next field, set PTR equal to that. Now PTR is either the index of the second node or it's null. And I'm exactly where I was a moment ago. So top of my while loop, see if it's null. If it is, I'm done. Otherwise, print out the next piece of data and keep going. And that's what we do in all these functions. print, search, delete, add, right? Every one of these, you got to start at the sentinel, you got to move through. And you can do it a variety of ways. This is one way. Okay, so search is almost exactly the same. Initialize PTR to the sentinel. While that's not null, instead of printing the data, see if it's equal to the number, and if it is, I'm just going to return 1. I'm going to kick out of my whole function right here. Otherwise, I'm going to set pointer to the index of the next node, or null, and I'm going to go back to the top. All right, let's look at delete, and add is the hardest. So delete, I'm using a pair of nodes, previous and current. And this first node is a sentinel. So I don't really want to look at its data value. So the first node that might be the one I want to delete is sitting right here. And the idea of deletion was, once I find a node I want to delete, I need to know what the node was before it, so that I can adjust its pointer to skip over this node that I'm deleting. So I'm thinking of this as my current node, and this is my previous node. And again, you can do this a variety of ways. You could do current and next, right? You could do previous, current, and next. I mean, there's lots of things, but whatever makes sense to you. For me, this is how I think about it. Here's the node I'm checking to see if I should delete. I'm going to call that current. Here's the node that came before it. I'm going to call that previous. So with that idea in mind, how do I initialize this? I got to say previous equals 0. So that points to the sentinel node. And I've got to say current equals previous, I'm just going to say dot next, but LL bracket previous dot next, or previous arrow next in a few minutes. So that's my initialization. And I'm going to end if I get to the bottom of my loop and current is the last node of my list. No, actually I'm gonna end if I've moved down. And now this is previous. And my current is null. In other words, I tried to move down from previous current to previous current, but current doesn't exist. So my while loop is just while current is not null. And check the current node's data. If it's equal to num, then we want to delete it. So have the previous node, that's previous.next, equal to whatever the current node is pointing to, that's current next. And if current next happens to be null, that makes the previous node point to null. That's perfectly correct. And then release the current node and return 1 saying success. Otherwise, move down the list, set previous to current, and set current equal to what current's pointing to. And if you get through this whole loop and you haven't found the node, then return a 0. All right, and get node and release node we've seen before. So let's look at add. So add's a little longer. So add finds the correct spot to insert the given number and performs the insert. If the number's already in the list, it will add a second copy. Well, that's good to know. And turns 1 on success, 0 if out of space. So I'm telling the user right now my add function does not check to see if this is a duplicate. So if you don't want duplicates in your list, you got to take care of that. Because if you call add, it'll just go ahead and put the same number in. So that's useful information. All right. So pointer to the sentinel node and the number. Same initialization as before. Previous and current are pointing to the sentinel and the first data node, respectively. All right, and I create a new node first off. So call get node to make a new node. If you're out of memory, go ahead and return the corresponding fail. Otherwise, initialize the data field. So that makes my new node. And then figure out where to insert it. Well, the place that you insert it is right before the first node that has a data value bigger than number. So current is the node that I may want to insert before, just like current was the node I may want to delete. So I check list current.data. If that's bigger than number, insert right before current or right between previous and current. And then this is, you know, ODP stuff. Have the previous point to the new, have the new point to the current, and return success. And if that's not the place to insert, move down the list, same as in delete, bless you. Previous is current, current is next. The edge case is you get to the end of the list. For delete, this means we just return 0, didn't find a node. For adding, if you get to the end of the list, and that's this situation here, previous is the last node, current is null, then none of the numbers in here was bigger than the number we're trying to insert, so we got to insert right at the end. So we simply want to take our new node, have previous point to the new node, and have new point to null. And that's exactly what we write in the code. List previous.next equals new, list new.next equals my null. And then return 1. So as soon as you can find harmony between what you want to do, what that looks like in terms of manipulating these nodes, and how you write C code to do those manipulations, you're done, right? That's 222. So that's what you're working towards. And we already looked at my stuff yesterday. It's just prototypes and the structure and my null. All right, so questions about this? So what does this mean for PA2? Well, PA1 initialization was supposed to set the sentinel node equal to null. In our main program, we declared an array of struct nodes, so there was already a place in memory for the sentinel. So init just sets the next field to be null and marks it as valid. So what do we have to do in PA2? So in our main program, in the assignment, it says you're going to declare your linked list to be just a struct node star. And you initialize it by saying something like list equals init. Sure, yeah, you could say struct node star list equals init. That should work. So what is init? It doesn't take any arguments, it returns a struct node pointer. And it's really just I don't know, make yourself a pointer to a struct node, malloc some space for it. So now S is pointing to an actual block of memory that can hold a struct node. And we want to set the data field to something that we recognize maybe. So this is, instead of list bracket 0 dot data, this is S arrow data. Whatever you want to put in there. And instead of list bracket 0 dot next, this is S arrow next. And instead of my null, it's null. And the main program in PA1 knows the sentinel is at location 0. It doesn't know that in PA2, so we have to tell it where this sentinel node is in memory. Well, where is it? It's at S. S is the address of that sentinel node. So we return S. And there's your init. So once you do that, and you set list equal to init, list will be a location in memory. And if you look at that location, you should see whatever data value you stored, followed by a null. And that's never going to change throughout PA2. This value of list is going to be fixed for the rest of the run. But the thing that it points to is going to change. When you add a node, it's going to point to that node instead of pointing to null. And if you delete the node it's pointing to, it'll change to something else, possibly back to null. Okay, let's look at the print function. So right now, we set up something to point to the sentinel. We set up something to point to whatever the sentinel is pointing to. And while that's not null, we print out the data field and we move to the next node. So let me put this down. Initialize pointer to what the sentinel is pointing to. If it's not pointing to null, print out its data and then set it to the next. That's PA1. Okay, PA2. And this is call the argument struct node star sent for sentinel. So instead of pointer being an int, it's going to be a struct node star. So what should we initialize pointer to? Sent arrow next. Right, we're being given the address of this. Sent arrow next is the contents of this next field. That should be the address of this node. So we say pointer equals sent arrow next. And then while pointer is not equal to null, so PTR is here right now. We want to print out the value of the data field. What is that? Yeah, PTR arrow data. And then we want to change PTR to be whatever's in the next field of PTR. PTR equals PTR arrow next. And on and on. So I don't want you to kind of mechanically just translate PA1 into PA2, even though that can be done. Okay, if you wrote PA1 strictly the way it was specified, you can actually go through and do a global replace in VI and change PA1 into PA2. But I don't want you to do that. But I'd like you to be thinking about that process while you're writing PA2. Be thinking about how what you're writing relates to what you wrote in PA1. The fact that this is moving you down the list just like this did. Right? This found the next field of the thing pointed to by PTR. This finds the next field of the thing pointed to by PTR. The algorithms should not have to change at all. Your add, your delete, your search, your print, this pseudocode, the algorithms for those should be identical for PA2. The only thing that changes is how you code up in C what you want to have happening on this picture. And it's a different language because now our Sentinel node is an address in memory.
I have a question on the print function.
Yeah.
Would it be frowned upon to do it recursively?
Yeah.
It would seem like it just makes it harder to read.
It makes it harder to read. It can blow up if your list is really, really long.
Hey, what?
It can blow up if your list is really, really long.
Overflow the stack.
Yeah, yeah. Or worse if you have like a circular list and you don't catch that. But we will be doing a lot of recursion, so you get a lot of chance to do that. Okay, so right, what does search look like? Struct node PTR equals list. Well, PTR is not equal to null. If list arrow data equals num, return 1. PTR equals PTR arrow next. Your search function. But like I say, try to be thinking about what it is that you're writing instead of just finding the pattern and doing that, right? Because we're not going to go back to using an array of struct nodes again. That was just for PA1. So everything else we do in this course, we're going to be doing this dynamic memory approach where we have pointers to memory and we dereference by using these arrows. So this is what we really want to get comfortable with. This is just kind of a way to introduce linked list without that extra machinery. And then get node is just a call to malloc, right? We don't have to set a valid flag to 1. We don't have to loop through. We just call malloc. And malloc will give us back an address. That's what we return from get node. So get node returns a struct node star instead of an int. And if malloc doesn't find any memory, it'll return null. And if we return what malloc gave us, then get node will return null.
Did we need get node and release node in PA2? Because the assignment details didn't say, so I just put malloc in add. If that was okay?
Yeah, that's okay. But the idea was if you didn't want to have to monkey around too much with the code and add and delete, you could just use these. But it makes more sense to just put it directly in, so that's good. Release node is just a call to free. So if lists is a pointer to a struct node that actually was something that got malloc, you can say free parentheses list, and it'll release the memory. If it's not a pointer to something that got malloc and you try to free it, it'll probably say false. But if everything's wired up correctly, right, the only time you call a release node, you should be passing it a pointer to a node. So that should work fine. All right, so let's talk about memory leaks. You have this linked list that you've built up by dynamically allocating nodes. And the user is asked to exit the program, and you need to free the memory associated with each of these nodes. Okay, so how do you do that? So pointer equals sent, right? That's our Sentinel node. I'm going to have another struct node star called temp. I'm going to set that equal to PTR. That's going to remember, so here's PTR. that's going to remember the node that I was currently looking at, and I'm going to change PTR to be the next node. Or call it previous current, probably makes more sense. In fact, let's just do that. Let's do previous and current. Well, if this is previous and this is current, what can I do? I can say free previous. Now this goes away, and every piece of that node is now considered inaccessible. As soon as I free this node, I don't want to say, let's look at previous.next, because that value might change immediately. So once you free a node, that node is gone. Okay? But I don't need previous next, because I know current is my current node. So I free previous, and then I change previous to be current, and I change current to be current next. And what have I done? I made this previous, and I made this current, and I can go back up here. Free to previous, that gets rid of that. Change previous to be current. Change current to be current next. Go back up to the top. Free the previous. Change previous to be current. Change current to be current next. Well, current is null, but I'm not done. I still have one node I have to free. So I'm tempted to come back up here again, free my previous node, which will get rid of this, change previous to current, change current to current next, but if I do that, I'm going to seg fault, because current is not a valid node. So you got to be a little careful how you wind this down. One thing to do would be to do a while loop while current is not equal to null, and then just remember that when you exit that loop, you need to do one more call to previous. Another thing is to put a statement inside your while loop that says if current is null, exit at this point. So there's lots of ways to do that. But basically you're walking down your list, and each time you take a step, look behind you, pick up the node you just left. And take another step, walk, look behind, take that node, do that. When you're done, you'll be standing on the last step. You just need to figure out how to get rid of that. Does that make sense? All right, we talked about valgrind, right? Just valgrind space, name of your executable program. Run your program normally. When you're done, it will tell you if you've got any memory leaks. We'll play with that a little more some other time. All right, let's talk about the quizzes. So quiz 1 you already did, that was January 8th. Let's take a look at quiz 2, which is opening up, which is closing very soon. So 5 questions. If you declare integer x32, how does the compiler treat the symbol x? What's the proper interpretation of y equals star x, assuming that x is a pointer to an int and y is an int? Consider the struct statement. What's the correct syntax for setting the x field of var to 0? Same struct statement. Var is a pointer to a struct. What's the equivalent of var arrow x? So that's just a definition. And then which of these will cause a seg fault, right? So think through these and what they're asking the system to do. And one of these should pretty deliberately give you a seg fault. So that's due on the 31st. So play around with that. But it's nothing you haven't already dealt with. And then quiz 3, this is the linked list one. So, and it's 5 questions, right? Which of the following is true about the memory in a linked list? What's the sentinel node in a linked list? How do linked lists compare to arrays? Thinking of PA1 as an abstract data type, which of the following would be a correct line of code in the main program? 3 of these are things you would not want to write, and that I might have commented on if you actually did write this. And then as an abstract data type, which of these would typically not be part of the interface to the linked list that the main program would deal with? So 3 of these would be appropriate, and 1 of them is questionable. So those you should be fine to do. And then the really interesting one is the GDB quiz. So this is due on the 5th, but you know enough to work on this. And we may take some class time. But let me get you started on it. So this is 10 questions. So question 1, start the debugger, set a watch point on I. Okay, so this is using a program called G1 /temp. And you want to run it with GDB. So how do we do this? GDB/temp/G1. Okay, it's been compiled with symbols. So you can get access to the structure definitions and the variables, but not the source code for the main program. Okay, so start the debugger, set a watch point on I, and continue until the value of I changes. Continue repeatedly until I equals 5. What's the value of X at this point? So how do we set a watch point on I? Well, first we say start, right? That begins the process of debugging. I can print the value of I, and it's some uninitialized value. I can print the value of X, and it's 0. Okay, you can step through your code and watch the value of I, but you can set it up to do that automatically. So just say watch I, and any time that I changes value, it should come back to the prompt and let you do things. So I wanted to run until I changes. So I'm going to say continue, and it runs, and it tells me it's at this location in Maine. That's a hex address, and the old value of I was crazy number, the new value is 0. And if I say continue, it'll run until it gets to line 22 of G1.C, and now it says the old value of I was 0, the new value is 1. And at any point, I can do things like print the value of X, print the value of I, and so on and so forth. Okay, so that's all you need for question 1. Question 2, how many bytes are allocated for the struct mystruct? So there's a structure in here called mystruct, and I want to know how many bytes the system is using to store a mystruct. Well, we don't know what mystruct is, right? We don't have source code for that. How do we figure out how many bytes it takes?
You just move a block of memory, like move my struct block of memory, and look for the hex values.
Okay, but we don't have a block of mystruct memory yet. Otherwise, that would work.
You just do print size of.
But we can use size of, right? And GDB understands size of. So I can print size of struct mystruct, 32 bytes. Now if I print size of struct mystruct star, that's 8. That's a pointer. Okay, this is where the star makes it confusing. So your goal is, there's 10 questions here. Your goal is to go through these questions using GDB to try to answer them. So what's the address of the variable named data? Well, there is a variable named data. It's something. It's an array of arrays or something like that. We don't know what it is. But we can find out where it is in memory. We can find out the location of any variable in memory. What's the symbol we use to find where something is stored?
X, right?
Ampersand,
X.
right? Just like what we do with a scanf.
Well, what is X then? Like examine element?
Examine, yeah, we could use X also, right. So it tells me that data is an array of 10 struct mystructs. And it starts at location 60, 10, 60. So now we know what these things are that we're seeing, and hey, we just found out something about the structure. It has fields named X, C1, C2, Y, F1, F, and Z. Okay, we're hacking this code. You got an executable, but fortunately it was compiled with debug symbols on. And with that and GDB, you can start reverse engineering this and start figuring out all kinds of things. Every now and then something gets released into the wild with debug symbols turned on when it wasn't supposed to be. And people go crazy over that. Because once you get a copy of it, they can't take it back, right? You can recompile it, but if you got a copy of it, you can do this, and you can find a lot of information about stuff. So an old PDA called Palm Pilot got released, and they put the -G switch when they compiled it. And it's basically like an early open source thing. There was speculation that it was deliberate. That they wanted people to basically have access to the source code so they could improve it and develop it, right? The idea of open source, but it wasn't really a thing at the time. So that was kind of fun. All right, so play around with this, right? Work through the instructions and see where you can get, and then bring questions, right? And this, I absolutely encourage you to work with other people, to talk to each other, but not in the sense of, you know, person 1 does all the work, persons 2 through 10 say, hey, what's the answer for such and such, okay? But get together and think about this, play around with it. It's a really good opportunity to get better with GDB and to start thinking about how this stuff is sitting in memory, how it relates to the code that we write. Because we write C code and it's very kind of, you know, 40,000 foot view. But data structures, the stuff we're doing in here, sometimes we have to get really down close to the metal. Right? We got to understand when I say malloc, what's that doing to the memory of my machine? When I say this thing, arrow that is equal to something else, what is that doing to the actual bits? And the more comfortable you get with that level of the system, right, the more success you'll have in late night debugging sessions and things like that. All right, that's all I got. I will see you tomorrow.